Okay, welcome to today's video. For this video, we're going to talk about what valence electrons are and what Lewis dot structures are, as well as how to draw Lewis dot structures. With that said, let's go ahead and get started for this video. Valence electrons are just electrons that reside on the outermost energy level of an atom. They are typically used in bonding with other elements. There's always some exceptions and some cases where they don't, and chemistry is always a little bit more complicated than as simply as we're putting it here. But just to give you the quick example, these are what valence electrons are. Hydrogen only has one energy level, and because it is the very first element in the periodic table, it's only got that one electron that resides on the outer level that it has, so it's only got one valence electron. Helium is the second element on the periodic table, so it has two total electrons. It only has that one energy level, so it has two valence electrons. Carbon is the 6th element on the periodic table, and because it's on the second row, it's got two energy levels, so it's got two electrons in that first energy level, and then 1, 2, 3, 4 in the outermost energy level of its electron orbitals. So these 4 on the outermost energy level would be its valence electrons. So carbon would have 4 electrons. Helium would have 2 electrons. Hydrogen only has 1 electron in its outermost shell. Now, when we talk about these valence electrons, we draw different diagrams to represent them. The most common is Lewis dot structures. In a Lewis dot structure, all you include is the symbol and the valence electrons. So this just shows the valence electrons. We don't have to include anything that is beneath that outermost energy level as far as electrons go. The only thing that we are looking at and we are focusing on is those electrons that get used in bonding or making lone pairs. Basically the electrons that allow an atom or a specific element to interact with another element. So hydrogen only has that one energy level. How you would draw it in a Lewis dot structure is just that one dot. Helium is a special instance. Normally we would go down the sides and around when we draw Lewis dot structures, and I'll demonstrate that in these other examples. But because helium has a complete energy level, it is the last element in its row. These electrons are not going to bond with other electrons and other elements normally, so we would draw it like this. And I'm going to elaborate on other examples. Looking at carbon here, carbon has 4 valence electrons, so we would draw that just 1, 2, 3, 4, going down the line there. Let's take a look at a few more examples. Another way that you can draw these Lewis dot structures of specific elements is by looking at what group number they are in. For the purposes of this, we are going to ignore the transition metals and the rare earth metals down below. We are only going to focus on groups 1, 2, 13, 14, 15, 16, 17, and 18, specifically in the upper column, these 3 rows going up here. So anything in group 1, because it is in group 1, it only is going to have 1 valence electron. So no matter if we are drawing hydrogen, lithium, or sodium, they are all only going to have 1 electron in its outermost shell. Now if we looked at the second row, beryllium, magnesium, and calcium, these all have 2. And I've seen these drawn different ways, where they're drawn one up here, one off to the side, one up here, one down here, to show that they're farther apart. But basically it just means that these 2 are available for bonding. Moving over to the other side here, over on this side, we'll take a look at 2 more examples here. Let's make that 3. So we drew an example of carbon earlier that goes down into silicon as well. If we looked at silicon, which is in the 14th, or we'll call this the new group 4 here, this also has 4 electrons in its outermost shell, 4 valence electrons, just like carbon does. So we would draw it like this. Nitrogen, which is 1 over in the 5th of these groups here, has 2, 3, 4, 5 valence electrons is what that means. And that would go for the same for phosphorus, which also has 5 in its valence shell. We'll look at 2 more examples here. We get over to fluorine and chlorine here. Fluorine in group 7 or 7A of these groups here that are not transition metals. Fluorine is 1 away from the very last row. So it's going to have 1 less than that, which is a total of 7. Same thing with chlorine. In that last row, they are all going to have the same number of valence electrons, with that 1 electron here available for bonding. These ones forming lone pairs. This would be a bonding electron. These would be a lone pair, normally non-bonding. Last example I'll look at, we looked at helium before. There is these noble gases. There's a rule called the Octet Rule, sometimes referred to as the duet rule, which it's just a way of saying that once an energy level is filled, none of the electrons will want to bond with electrons from other elements because they will all be lone pairs. So we'll talk about that in another video, but basically these are bonding electrons. They will be used to bond with other elements, the electrons of other elements. Phosphorus can form up to 3 bonds, whatever those bonds may be. Silicon would form up to 4. Chlorine would form up to 1. But if we looked at helium, it only has those 2. Neon, because it's in that 8th row, helium being the exception here, neon is going to have a full 8 electrons. All of these lone pairs, none of them able to bond with other electrons. The same is true for argon. And krypton and xenon and radon going down. Short disclaimer, all this stuff is always just a little bit more complicated. The question was posed, which is stronger, a covalent bond or an ionic bond? And the answer that was given after much debate was, it depends on whether or not you're in a vacuum or something like that. And we are focused here on the basics. So I hope this was a little bit helpful in drawing Lewis dot structures. If it was, leave a like and subscribe. And I will see you guys all in the next one. Peace.